Greetings, you all. I'm going to present the paper, Classification and Clustering of Sentence-Level Embeddings of Scientific Articles Generated by Contrastive Learning. So the agenda here, we have the background of the research, the methodology. Next, I'll present the experiments, and later I will discuss and present the results. So the background here is that the dissemination of knowledge in scientific community is mainly by publication of articles, also known as papers. And papers, they share a common structure. Generally, they will have a background which describes the problem and the motivations for conducting the research. Also the objective that contains the purpose of the research, the methods that detailed all steps conducting in making the research, and also they're necessary to guarantee reproducibility. And finally, the results that reports the findings. So in order to understand research, these are the key subjects that we need when performing a systematic review. These are the key subjects that we have to assess when conducting a systematic review. So our objective here is given a scientific article, a paper, to classify each sentence of this paper into the labels background, objective, methods, or results. Our proposed solution here is to train a sentence transformer model, which is a neural network, a deep neural network with contrastive learning, and using the output embeddings to train traditional classifiers such as MLP, KNN, and so on. So in this research, we represent a text as an embedding. And for those who are not familiar, what is an embedding? Embedding is a way to represent a text as a fixed size vector of real numbers. You can also generate embeddings using neural networks for image or sound. But here in this work, we are using an embedding to represent a text, in this case, a sentence. So these embeddings, they can be learned by training a sentence transform model on a textual dataset. And to evaluate our approach, we compare these fine-tuned models with the contrastive learning with baseline sentence transformers models that were not fine-tuned with contrastive learning. So we raised three research questions. The first one is if the fine-tuning sentence embeddings for clustering outperform the non-fine-tuning embeddings. The other one is that to assess the performance of traditional classifiers, if they improve using the fine-tuning embeddings as opposed to no fine-tuning embeddings generated by the baseline models. And the last one, we also compared these fine-tuned embeddings with contrastive learning with deep learning models that were fine-tuned directly as sentence classifiers. So our methodology here, I'll give an overview first. It's comprised by two stages. The first one, we fine-tune a sentence transform model with contrastive learning. Then we train classifiers with the embeddings. We train two models. One with the embeddings generated by the baseline models that were not fine-tuned. And we train other models with the fine-tuned sentence transformer models. And we evaluate these on the test sets, these models. So the first stage, which is fine-tuning. So we have a data set of labeled sentence. So we have a sentence and the label that can be background, method, objective, or result. And we generate sentence triplets. Sentence triplets, they are necessary for the contrastive learning. So here I'll also give a little an overview, a high-level explanation of how contrastive learning works. So our data set has samples in the following format. We have an anchor. I have A is an anchor sentence. P is a similar sentence to A. So we call this a positive sample. So this means that these are two sentences that are from the same label. So we pair them together. And N is a negative sample, meaning that it's a sentence that has a different label in respect to A and P. So once we generate this data set of sentence triples, we can fine-tune our transformer with contrastive learning. So to fine-tune our sentence transformers models with contrastive learning, we use the triplet loss function that this is the contrastive loss function, the triplet loss. So here we have the distance between the anchor sentence and the positive sentence. We calculate this. We can use the Euclidean distance, for example. And we have here the distance between the anchor sentence and the negative sentence. And so we want to maximize this in a way that the anchor sample and the positive samples, they get together in a vectorial space. They get closer, and we want to push the negative sample away in the vectorial space. So in natural language processing, we can also call this the embedding space, but since embedding is a vector, it's the same as a multidimensional vectorial space. So this is the first stage. The next, to evaluate our approach, we use the fine-tuned transformer. We encode the sentence. So we take the sentence, the text of the sentence, the string of the sentence, and we encode them using the fine-tuned transformer. So in this way, you generate the embedding, which is this vector representation. So then we have a pair of an embedding, which is a vector of features extracted by this fine-tuned transformer. And we have the label that can be background, methods, etc. For clustering, you can use directly the embedding. We don't need the label for that, since clustering is an unsupervised learning. So we train these classifiers using the sentence embeddings and the label that comes from this data set of labeled sentence. And here we use directly the embedding for clustering. We also created in this work a data set that was extracted from the full text of papers. So we use the section heading, the title as the label. So if you have a corresponding section with the heading method, so we take the sentence there and we consider it as being from the label methods. And we were able to extract that from more than 1,500 articles, and we have more than 170,000 labeled sentence. So we created this data set in our work, but there exist others already labeled data sets like PubMed with 20,000 papers. But these two data sets here, the papers came, the sentence come from the abstract, not from the full text of the papers. And also there are some differences in the labels here, and these data sets have the conclusion, but you don't have here. And also this data set doesn't have the order label, but that's very important because not all sentences in a paper will belong to these labels. We have the order. Sentences that are neither background, objective, or methods or results. Okay. Another thing that's important here is the domain. So we know that from the scientific literature that transformers or deep learning models in general, they can be very sensitive to the domain of where the text is being driven for. And now I'm going to explain and present our results. So we take two language models to fine tune. The first one is CyBERT. CyBERT is a pre-trained transformer model that was pre-trained in more than 1 million scientific articles. So this is a BERT model that was fine-tuned in the domain of scientific articles. And the all-mean LAM, this model is in size, in numbers of parameters, is smaller. This is small compared to CyBERT. And it is also fine-tuned, pre-trained in a generic domain. So it's not for the scientific domain. So we chose CyBERT because it's from the scientific domain, and all-mean LM because it's smaller. So it's faster to train, has less parameter, so you don't need a very big GPU memory to train it or even to make inferences. So I want to test a very efficient model as well, even if it was not from the scientific domain. And we used the sentence transform library, which is called SBERT, which has a loss function, which is the triplet loss, but this is called batch or triplet loss. So in this, using this loss function, so the sentence triplets, they are generated online every time the process is going to create a batch for being processed in the fine-tuning process. So you just need the sentence and the label, and then the triplets are created in an online manner. You don't need the samples, the sentence triplets as a data set. And for clustering, use k-means. And to the classification, we trained a decision tree, KNN, MLP, random forest, and SVM. So to evaluate the clustering, we have used clustering agreement measures, such as adjusted rand index and adjusted mutual information. So these are measurements that compare a known and a generated partition. So if we have a labeled data set, which is the case, a test labeled data set, so we have a sentence and its corresponding label, such as method, results. So we have a known partition. Once we generate the clusters for this sentence, we can compare if the sentence are belonging to the original clusters of the test data sets. So these agreement measures are going to see how well this generated cluster with an unsupervised training compares with the real clusters of the generated in the test data set. And also use a silhouette score which is a measure that compares the cohesion between the samples within a cluster and the separations of clusters. So here are our results. So here we have the 3 data sets. We have here the 3 metrics that we use. Here it's MinLM and CyBERT, which are our language models. Here in bold, we have the baseline and the fine-tuned models. So the bold values represent the highest value within each language model, and the bold and underlined the highest value in the data set and that metric independently of the language model. So we see here a huge improvement into clustering, and that was expected, because when we are performing contrastive learning, we are rearranging the embeddings in the vectorial space, and clustering acts, this algorithm, k-means, acts like computing the distance between the samples, the vectors in this case, and creating a separation between the samples using this distance. So contrastive learning is an ideal approach for that here. And so here's the visual representation. So here we have the CS abstract. These are all samples. When we use the baseline, the non-fine-tuned models, we have this situation. So the samples are distributed in a 2D space here. This way, once we fine-tune, we see here these samples are rearranged in the vectorial space, the vector space. So here we see that samples from the same label, they get closer. And in PubMed, we see this very clear here. So we have samples, these red dots here. They are inside this other cluster. So we see a very good separation here once we fine-tune our models with the fine-tuned models. These are the results of our classifiers. So here we have the sentence transfer model, MinLM and CyBERT, baseline and fine-tuned, and here the classifiers. Here are the 3 data sets. So once again, we have the bold values represent the highest value within each sentence transformer model, and the underlined value, the highest value, comparing all independently of the sentence transformer. So we also see here improvements comparing the baseline and the fine-tuned models. So here we present a comparison between all these results. So here we have MinLM. These are the 3 data sets we use. So for CS abstract, the best classification model was random forest. The fine-tuning model had a F1 micro. Oh, I forgot to talk about which metric you use it here. So here we use F1 micro. In this case, it's equivalent to accuracy. So we have a 75.02 and the baseline 55.37. So the difference here, it was an improvement of 35% comparing the fine-tuned with the baseline model. So on average here, we have a 30% improvement. We also presented here the standard deviation to see if there is any outlier here. We cannot, I don't know if we can consider these an outlier, but we see this show a great improvement, and this is almost the half of these other ones here. But we're talking of different data sets anyway. And here we have the CyBERT. So CyBERT here, SVM. It's different here for this data set. And we also see an improvement between the fine-tuned and the baseline models. And let me go back here. So KNN is a classifier that works with the distance between samples. So if these two samples are closer, this means that they belong to the same label. That's how KNN, this is a very high level explanation, but that's how it works. So since contrastive learning works by rearranging all the samples in the embedding space, so KNN is one of the intuition is that KNN, it's going to be one of the algorithms of machine learning that will best benefit from contrastive fine-tuning. So we wanted to compare the performance of the fine-tuned and baseline models only in the KNN classifiers, right? So we see here that all of them had a great improvement, and we also compare it with the best model. So here we have the best models, the best classifiers. So we use these values here to compare, okay? So we see here that in average, the KNN was only 0.40% below the performance compared to the best models here. So although random forest here had the best performance, we see that KNN is right behind. So yes, KNN is very benefit from the contrastive learning fine-tuning. And we also compare the best models with CLS fine-tuned language models. So in this case here, we take MinLM and train it not as a sentence transformer, but directly as a classifier. And in this case, we take CyBERT and fine-tune it directly as a sentence classifier. So we don't generate the embedding and use a traditional model for training. This end-to-end, we are using the deep learning model. So comparing these two, we see that our fine-tuned models, meaning that if you take the sentence transformer model, you train it with contrastive learning, has a best performance, then train it directly as sentence classifier, and that's we see here that it has a best performance than all the fine-tuned models here. And well, the downside here is that in our approach, you have to have two models, right? You have to have the deep model to generate the embedding, the sentence transformer model, and you also need a trained classifier like random forest. So you need two models, and in this case here, you only need one model. Okay. So now I'll talk about our conclusions and future works. So the first thing we saw is that CyBERT has the overall best performance in comparison to MinLM. So the thing here is the dataset used in fine-tuning in pre-training CyBERT has a large impact. So CyBERT is a BERT for the scientific domain. So this has a large impact. Also because all the vocabulary of CyBERT is the vocabulary of scientific domain. So if we're using papers to structure sentences, this has a great impact. Also that CyBERT support input sequences of 112 tokens, while MinLM only 384. So this means that we can have sentences of 512 tokens. It's pretty rare to have sentences like this because it's a huge sequence, but it supports, and MinLM supports less input sequence. So if we have a sentence which is greater than 384 tokens, then it's going to get truncated in MinLM. And we have positive response to our research questions. So fine-tuning improves the clustering performance and also improves the classifier's performance. And also that fine-tuning with contrastive learning outperforms the CLS classification, meaning that CLS classification is when we take a deep learning model and train it directly as a classifier instead of using contrastive learning. For future work, we want to work with large batch sizes. This impacts greatly contrastive learning. In this work, as I mentioned, we used a contrastive learning function that generated the sentence triples online. So if we have large batch size, we can generate more sentence triples to train. And use other contrastive loss functions, and also apply a method to enrich the semantics to generate the embeddings, like a large context. Here we are using only one sentence, but we can take an excerpt of text to get a large context, since transformers use the attention mechanism. So if we have a large context, we believe that we can improve the performance of our for training. So thank you.